Visible to all of you?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, very nice. So let us continue our discussion on the pulse width modulation techniques. So what we are basically discussing now is how to decide which PWM technique is suitable for your work. So which means there has to be some way to judge your PWM technique. So first we have seen that we need to have sufficient degree of freedom so that we can decide that at least some things can be managed. So you should have freedom to get your fundamental component or the modulation index with multiple options, and then among those options you need to choose the suitable one which gives you some suitable performance. So what is that metric over which we measure the performance, that you will see today. So now here we have understood, right? If we take two switching angles at least in the quarter cycle, that is bare minimum. So it gives us the freedom that we can choose several points corresponding to the same modulation index. So that's what we have seen over here. Now we are slowly trying to understand what can be done with the harmonics. So then we understood that what is called as which harmonic we should be actually concerned about. So because the induction motor, if you go by harmonic model, it is more or less the leakage inductance only, the total leakage inductance, which means the rotor plus stator. And in effect, this gives the attenuation of the order 1 by n for any particular current harmonic with respect to the voltage harmonic. Now, in our low switching frequency PWM, we have some order 1 by n associated with the harmonic voltage as well. So this gives much better performance for any higher harmonic compared to a lower order harmonic. So this is what we have seen, and similar thing can be extended for basically grid connected or any other system, let's say PMSM. So similar way we can apply superposition and we can find what is the current flowing into the system. So whenever we have different frequency voltages connected across any system, so we need to apply superposition because omega 1 is not going to interact with omega 2 and vice versa. So we need to have two different circuit realizations for solving this, and the current corresponding to both voltages we need to add simply in a phasor sum manner. So of course the phasors will also be moving at different speeds, so that also we need to take care. So up to this point the things are clear to all of you?
Yes, sir.
Okay. Now let us move towards the next stage where we understand that what can be done when we have multiple options for our fundamental component. Okay, let me take here for example. We have seen that the PWM technique may have several forms. Let us say A to B is one PWM technique, then C to D is another PWM technique, or there could be this G to H, this continuous kind of PWM, this coming over here actually and then going down, or E to F. Now which one to choose? We have plenty of options. So the easiest thing should be, or easiest thing could be, that you try to eliminate the most dominant harmonic in the system. So when we talk about the three-phase system, which are the harmonics present in the system?
The fifth, seventh.
That's all.
Dominant.
So when we talk about three-phase system, we have typically 5th, 7th, 11th, 13th, etc. coming over there. Triple N harmonics are gone and even harmonics are missing. So we have only these harmonic, and among that we see that these are kind of dominant. So 5th we can say is the most dominant. Then second most dominant could be 7th and so on. The order goes like that. Now what we can try basically, we can try to eliminate at least, let us say we say that okay, we don't want any 5th harmonic in our system. So meaning is that we will say that V5 is equal to 0. So we know that the expression for any nth harmonic component, and this is normalized with respect to the maximum amplitude what we can attain 2 VDC by pi. So I will write this expression. Understanding my point? So this is what we can say, that if we want the fifth harmonic to go to 0, then actually we need to solve this expression. And in effect we have this, or you can say that the 2 cos 5 alpha 1 is equal to 1 plus 2 cos 5 alpha. This is basically, it's not a linear equation, of course. So solving directly may may take a lot of effort. So what we do basically, how to solve this equation is that we can plug in some values of alpha 1 and we can compute the corresponding value of alpha 2. So if there is any possible value of alpha 2, we will get that. Correct. For example, let us say if I fix, okay, now we know that the alpha 1, alpha 2 are constrained by this. Alpha 1 and alpha 2 can be realized in this manner only. This inequality constraint is governing the operation of converter. So let us say we take alpha 1 equal to 0 degree. Now, what could be the possible solutions for alpha 2? So if alpha 1 is 0 degree, then this means this is 2, and then in effect we have cos 5 alpha 2 coming as 1 by 2. Understanding my point? So which means what? 5 alpha 2 can be 60 degree, or it can be 360 plus minus 60. So 300 degree, 420 degree, and so on. Because alpha 1 is 0, so any of these values are valid, whichever falls within 90 degree. So this inequality must be satisfied whenever we are solving this. So alpha 2 is coming out to be 12, then 60, then 84, and so on. Right? Several solutions we are able to find for one given value of alpha 1. And all three values are within 90 degrees. So these are all acceptable values. Similarly, if you take, say, alpha 2 equal to 90 degree. So what solutions you will find for alpha 1? So plug in the value in this expression. So you will have again cos 5 alpha 1 equal to 1 by 2. Understanding my point? Now the options for 5 alpha 1 could be what? What options could be there? Yes, yes, speak up. You have your calculator?
60 degree,
Hmm.
84 degree.
So first of all, this is 60 degree, then again 300, then again 420, and so on, right? These values are possible. Now, among all these values, we know that this alpha 1 is attaining 12, 60, 84. Still, all these three are valid because this is within 90 degree and alpha 2 is at 90 degree. So all these values are below alpha 2. So this is also valid solution. So again, we took one value of alpha 2 and we are finding multiple values of alpha 1. Now, let me say that, okay, if you introduce another number, say alpha 1 is equal to some 24 degree. Now, what is the value of alpha 2? What are the solutions for alpha 2? Yes.
Zero.
36, sir.
I am not able to hear. A little louder.
36.
36 degree. Any other option?
No, sir.
Okay. So this is kind of unique solution you are getting corresponding to 24 degree. Now, if I say alpha 2 is, let us say, 84 degree, then what is the possible solution for alpha 1?
No
It's a zero
solution.
degree.
Hmm?
No
It's a
solution.
zero.
No, I'm not getting. What is the answer?
Sir, it doesn't have any solution.
For alpha 1 equal to 84, is it?
No, sir. Alpha 2 is equal to 84.
Yeah, alpha 2 equal to 84. There is no solution, is it?
Yes,
Yes,
sir.
sir, it is coming 0.
Coming?
0, sir.
Okay. What is happening to this? Okay. Yeah, okay, let it be here. Okay, let us see. So you have 1 minus 2 cos alpha 1, 5 alpha 1 plus 2 cos 5 alpha 2 equal to 0, right? Alpha 2 you are inserting as 84. So what is 5 alpha 2 corresponding to that?
420.
420. What is cos 420?
1 by 2.
1 by 2. So,
0.5
0.5 or minus 0.5?
plus
360
Plus
plus 6.
0.5, sir.
Yeah.
plus
Okay, fine. So 84 and this comes out as plus 1 equal to 0. So you have 2 cos 5 alpha 1 is equal to 0, right? So alpha 1 is coming as some 18 degree. Is not that?
Sir, 2 cos 5 alpha 1 equal to 2. Sir,
Equal to
2.
so
1 plus
okay. Sorry, I missed here. Okay, yeah, maybe I have done the calculation mistake perhaps. Okay, so this becomes as cos 5 alpha 1 is equal to 1, right?
zero.
This is correct.
Yes, sir.
Yes, sir.
Alpha 1 is equal to 0 degree, you are saying.
0 degree.
Or any other option could be there or not?
So that 5 alpha 1 0 2 pi 4 pi.
72.
Is there or not?
Yes, sir.
Yes, sir.
Correct. So this is the solution, right? We have to see all the feasible solutions which are coming over there. Understanding my point? So you cannot just take one value and say, okay, this is the, and this is also not, it's not like it doesn't have any solution. This is a valid solution, 0 degree. Okay, let us try to mark these numbers on this graph. Okay, first number what we have found corresponding to alpha 1 equal to 0 is something like 12 degrees. So this is 15, 12 is something say here, and 60 and 84, right? Correct, right?
Yes.
Speak.
Yes, sir.
Yes,
And
sir.
then corresponding to alpha 2 equal to 90 degree, you have found something like 60.
60.
And then what else was there? 12 and 84. Correct. So 75, and then this is somewhere here. Then I asked what is the solution for alpha 1 equal to 24 degree. There was one unique solution that was 36 degree. So 30, 45 say somewhere here. And this is also 15 and 9 somewhere here, let us say. This is unique solution, correct? Here what you are finding is that the solution 84 is found here as well. When you are having 72 degree or 84 degree for the alpha 2, you are finding the solution as 0 and 72 both, right? So one is already marked here, another is here. Now, if you join these dots, you may have more points obtained on this in between the, so let's say you can vary alpha 1 to 10 degree and then search which are the solutions. So you will see that this is forming a smooth curve, something like this. So what is the meaning of this is that if you are operating on any such point, what you will have effectively, the fifth harmonic will be 0. So you can visualize this thing on the graph, and now you know how your fundamental component is going to come over there. This corresponds to m equal to 0. And this line corresponds to m equal to 1. Any other curve in between gives the intermediate value of fundamental component. You understand my point? So, which means to say that if let us say we are trying to eliminate the fifth harmonic, we know that for a particular modulation index, what options I have for eliminating the fifth harmonic component. Are you able to see that? So all
Yes, sir.
these points which are there at the intersection of a particular modulation index and V5 equal to 0, these points will give you a fixed modulation index. Say V1, at some V1 star, you are running the motor, so fundamental has to be fixed. And then V5 equal to 0. So there could be these solutions on which you may try to run the motor. You understand my point? This is basically what we know as the popular PWM technique, which is called as selective harmonic elimination. What it says that selective harmonic elimination, as the name is also clear, selectively you are eliminating a particular harmonic. But there are conditions. The conditions are your fundamental should be fixed at a desired value. It cannot be random. First condition is that. Then the harmonic which you want to eliminate, say fifth harmonic. So this is second equation. And then the inequality you are having for alpha 1 and alpha 2. So these three equations must be solved to get this selective harmonic elimination PWM. Understanding my point? Now somebody may say, why fifth harmonic? Let us say I want to eliminate seventh harmonic. So yes, we can have different SHE PWM technique, which is like having this property. This is another PWM technique which falls under the broader name selective harmonic elimination. You understand the point? Now question comes, can I eliminate more than one harmonic? Why just one harmonic, V5 or V7? Can I eliminate more than one? Then the situation comes back to the,
Sir, for V7, 3 switching angle.
yes,
Alpha 1, alpha 2,
exactly.
alpha.
So when we are talking about our pole voltage, we need to see how many degrees of freedom we actually have, which means how many independent switching angles are there within this quarter cycle. Because any other switching angle is dependent on this due to symmetry and other conditions imposed. So these are actually not independent of alpha 1, alpha 2. But when you have two independent switching angles, you have the flexibility that you can maintain, let us say, fundamental at certain value and eliminate any one harmonic. You understand my point? Are you getting this? For example,
Yes, sir.
if you try to eliminate both fifth and seventh with just two switching angles in the quarter, how your graph will look like? Little bit clearer picture. Let us see how it looks like. So how to rotate this? Okay, it's not moving at all.
Sir, and below there is one rotating symbol is there.
This is, yeah, now it is there. Okay. Which one? This one? This is undo and redo.
So control R.
Okay. Sometimes traditional solutions are better. Fine. So see here in this graph, actually, I have just plotted it through, this MATLAB code. So just to understand a better, view of what we are having. So green curves, what you see. Okay, first these black lines which are there. This you understand. These are corresponding to different modulation index, all the way going from 0 to 1. So this is what we are having. Now the green dot, what you see, this corresponds to every solution which is giving me fifth harmonic equal to 0. This is what we have got, right? So we have multiple options. One graph is here, another is here, another is here. Similarly, I tried to have, say, V7 equal to 0. Similar manner, I can vary alpha 1 and then get the value of alpha 2 corresponding to that. So this red curve, what I have got, basically corresponds to all the points or solutions which give V7 equal to 0. This is smooth, it's not discontinuous. So these all form basically some concentric contours. Okay, closed contours it will form. Now we are getting some solutions on this side of the graph as well. So obviously we know that because our modulation index is 1 here and then going to 0. So what this zone corresponds to is basically a negative modulation index. So certainly when we are running our motor, we are not going to switch between the positive modulation index zone and negative modulation index zone. So we will ignore this part as well, which means all these solutions which are available on this part are of no use. Correct. We have to only remain restricted to this part of the graph. Now you pick up any modulation index and you see that can we eliminate two harmonics together? This possibility is there only for m equal to 0. Only for this point, the two graphs V5 equal to 0 and V7 equal to 0 are meeting. Any other point, this possibility is not there. These both have deviated a little bit, by the way. This is only a little bit thicker dot, so it is looking like that, overlapping, but it's actually not like that. These have deviated. So somewhere our degree of freedom is related to how many harmonics we can eliminate. So if we have just 2 degrees of freedom, which means we can manage the fundamental and remove only one harmonic. Now whether you choose to eliminate 5th or 7th or 11th or 13th or any other harmonic, it is your choice. Understanding my point? If you want to include more harmonics in the elimination, so you should have more degrees of freedom. For example, if I go for 3 switching angles per quarter, I have, let's say, alpha 1, alpha 2, alpha 3. Here, so now I have freedom that I can eliminate 2 harmonics apart from maintaining this value of fundamental at the desired number. So for example, I can say that V5 and V7 both are going to 0. And then I am maintaining this. And of course, the inequality is valid here as well. Now the situation is 3-dimensional, right? So we cannot visualize it here on the graph paper and all. So, but through equations, we can understand that yes, there is possibility. We have 3 degrees of freedom. So in general, we should be able to do this. We are simply extending whatever 2-dimensional plots we have seen to the next level. Now, if I generalize the selective harmonic elimination PWM technique, in general, if let us say you have n switching angles in the quarter cycle. And when I say n, these are all independent. There is no condition given for the switching angles here. There is no predefined condition given. So say there are n switching angles total. Okay, let me write in capital N to differentiate it from the harmonic order. Okay, so if I have n switching angles within the quarter cycle, I can have my fundamental at the desired value and I can eliminate total n-1 voltage harmonics. And the inequality will still be valid. This is the general selective harmonic elimination PWM, also called as SHE PWM. This is in general true for any n switching angles PWM, where we are maintaining all the symmetries. Sometimes people try to abolish some of the symmetries and then they try to get more harmonics which can be eliminated. That is a different scenario. Here we are maintaining all the waveform symmetries. Waveform symmetries are intact. These are not disturbed. And then we have this condition. So in general, what we will do, we will solve these equations. All these n equations plus this inequality, this we will solve. One is this, and then we will have, say, V5 equal to V7 equal to V11 equal to V13 and so on. All these going to 0. So all these n-1 equations for the harmonics, capital N-1 and V1, this together will form this set of n equations you will solve considering this inequality to get the selective harmonic PWM. Understanding my point? So this is one technique, right? So now if we just visualize on this graph how my SHE PWM technique will look like, where am I moving on the graph? So see, simple solution could be that, okay, if I want my fifth harmonic to go to 0, what I can do? I can simply follow this curve. And then whenever it ends, I simply go in a straight line form and meet the final modulation index. This could be one PWM technique. Now another PWM can say like, why this? I can have this followed and going all the way up to this point and then drop from here to the maximum modulation index. This could be another PWM technique where I am following this path. The switching angles are different, right? That's why it's a different PWM techniques, all falling under the same name, SHE PWM. Then somebody may say, why fifth? If I want to go for seventh, So I can follow this red curve. I can follow this and reach up to the modulation index here, and then I can go towards the highest modulation index without any problem. Similarly, the other option for V7 could be I can start from, here there is gap. So I need to start from here in a straight line form and then follow this curve and then go to 0. So this could be another PWM. PWM4, let us say. So different ways you are realizing the same thing, which is called as selective harmonic elimination PWM. Now, of course, if you talk about V5 equal to 0, there are two options. And the fact is that both the solutions are not same. So not same in what sense? If you observe this path A, let us say, and this is path B. So path A is going very close to V7 equal to 0 for a lot of modulation index range. Whereas here, this is very far from V7 equal to 0. This means path A is going to see a low value of V7. And path B is going to see high value of V7 for most of the range. You see here. So to compare these techniques with each other, we should have another way to measure what is happening in the induction motor or what is happening in the circuit. Understanding my point? So here comes the next metric, which is called as, it's getting stuck again. Okay, fine. Yeah, the next metric that comes, that can be called as the total harmonic distortion, THD. And where we are talking about this total harmonic distortion, we are talking about the total harmonic distortion in current. It is not for the voltage, because current is our final product, final outcome. The final outcome is current. If current is good, then we are fine. So we know that dominant harmonic, let's say we have eliminated V5, then the dominant is 7. So if I am able to keep 7 within a low value, then I am going to get a good value of this. Understanding my point? So now, before proceeding further, let us see some more options, and then we will discuss a little bit about ITHD. Okay, now another possibility, let us say, when we are talking about the distortion, we will very soon understand what do I mean by that. So see, someone may say, okay, when we are more concerned about the distortion only in the harmonic current, then why to eliminate both? Can we not have low values of both 5th and 7th? I can have, right? If you travel somewhere along the middle of the two curves, you are able to maintain low values of 5th and 7th both for a very long time. For a good range of modulation index, you are able to maintain very small value of 5th and 7th both. So perhaps this may perform better. So this is where limitations of SHE PWM started coming up. What are the limitations? The limitations are, first is that it is giving multiple solution corresponding to any modulation index. So if you take, for example, 0.4, then one solution is here, another solution is maybe here. Understanding my point? First limitation is, why this is limitation? Because it is not unique. The solution is not unique. So you need to choose. So you need another factor on top of your solution, which will decide which one is better. So this is one limitation. The second limitation is that there is lot of gap when you move towards the higher modulation index. You have no solution. So many a times when we go close to the higher modulation index, there is no solution available. Then what to do? We are forced to move in any manner, whatever we want. And in all such cases, in all such modulation index range, we will not have this condition fulfilled. V5 equal to 0 or V7 equal to 0. You understanding my point? And another issue is the third problem what may occur for some of the solutions, that if you eliminate one harmonic, for example, fifth you have eliminated here and seventh is too high. So another harmonic may shoot up. In effect, what may happen, the performance what we are trying to make good may not be as per the expectations. Understanding my point? So this is where people come up with methods which are beyond SHE PWM. So what they say, okay, I will not eliminate these harmonics. What I will do, I will try to have, let's say, sum of few harmonics going to minimum value, not zero value. So for example, I can say that maybe I need to delete some of the things from the next class. It's becoming very bulky. So say I take a factor VH, and which is basically kind of RMS value of this fifth and seventh harmonic both. Something like this. Now this factor I can try to minimize. I am not eliminating anything. So I will maintain my fundamental at some value and I will try to minimize this factor. So of course, when we are saying that we will minimize this, we are giving weightage to both the harmonics and equal weightage to both the harmonics. So that condition may occur somewhere in the middle of fifth and seventh harmonic zero zones. No, these curves are giving zero. So somewhere in the middle it can be there, and then moving on this side. So it can be here up to say this point. Okay, it's getting stuck actually today. Yeah. So let's say if what is happening? Yeah. If I have to minimize that, I can move up to this point on this path, and then I can deviate from there and I can go in this zone. Understanding my point? These two places what you have basically fifth and seventh both are coming close to zero for longer range of modulation index. Fine. So this could be another PWM technique. Now these techniques where we are not trying to eliminate any harmonic, rather we are trying to minimize a factor. Now this factor could be having more harmonics. Let us say you can take sum of all harmonics. No, this let's say I keep n. So n may be 5, 7, 11, 13 and so on up to 25. A wider range of harmonics. This could be my factor to minimize. So this gives up, or this gives out a new PWM technique which falls under the optimal PWM technique. Where we are not trying to eliminate anything, and because we are minimizing, certainly we are going to have a solution, and that solution is going to be unique. Because we are minimizing, we are only getting the minimum value. It does not say 0 or any particular number. So whichever is minimum, and always it's going to be unique solution for the complete modulation index range. So that's why somewhere optimal PWM techniques perform much better compared to SHE PWM. Now, as I said earlier, our outcome is current and not voltage. Voltage is only input, right? So we should be more worried about the current. So what I can say, okay, I do not want to have minimum value of certain voltage harmonics, but I want to have minimum value of certain current harmonics, or I capital N, let us say. I want to minimize this. So N you can take as 5th, 7th, 11th, 13th, and so on, wherever you are happy up to whatever point. You can consider that. So this could be another way. I want to minimize this. And other equations are also valid. Don't forget that. This V1 having a fixed value and the inequality constraint. These are all still valid. Only I am having this optimization problem over here. Understanding my point? Now, this is where we come up with something which is more, it's kind of giving the property of the system in terms of how much current you are drawing in the fundamental. Let us say this does not say anything about what is the number with respect to the fundamental. Say you are drawing 5 ampere or 10 ampere or 15 ampere, this number will remain same. So something which is more relative to the fundamental current that we need to have, and which is what is called ITHD. So what this says basically, this is ratio of this sum of all the harmonics and the fundamental. So this can also be written as in a different manner, total I RMS square minus I fundamental RMS square divided by I fundamental. This is another way of writing it. Now this n, when I am writing, this n is certainly not equal to 1, and n is going in a manner 5, 7, 11, 13 and so on. Understanding my point? Yes or no?
Yes, sir.
Yes, sir.
So
Yes, sir.
my optimal PWM could be that I want to minimize ITHD instead of any voltage harmonic or any other thing. So this could be minimize ITHD while keeping other equations intact. V1 is having a fixed value, whatever we want based on our V by F or any other control, and the inequality. Now, this does not say that how many minimum switching angles you should have in the system. SHE PWM was suggesting that we should have at least sufficient degree of freedom, whereas here there is no such constraint. This could be possible only with 2 switching angles as well. So switching angle is not limitation for optimal PWM. And we are going to find unique solution for every modulation index, and we maintain the inequality. Correct? Now, when we talk about ITHD, we know that this is good number to consider, but when you are designing a system, this is turning out to be a load dependent quantity. Everywhere it's current, which is dependent on the load, right? Fundamental is also dependent on load. Then harmonic is also dependent on leakage and other factors which are associated with load. So somewhere you need to know what is the load you are going to have to minimize these factors. So let us just try to rearrange these numbers. So what we have, ITHD going equal to, say, sum of I5 square, I7 square, plus I11 square, plus I13 square, and so on, and divided by I1. Now we have seen that in general, our current harmonic IH and voltage harmonic VH are related by this. The magnitude is related through this leakage and the harmonic order. So we can plug in these values here. Okay, some difficulty here. Okay, fine. It's behaving a little bit weird today. So then I can replace every harmonic with the corresponding voltage harmonic. So what I will get in general is that, say, summation of n not equal to 1 in square, which is divided by I1, and this is going equal to summation of n not equal to 1 Vn square divided by n omega L whole square divided by I1. Now this omega L factor is basically common, so we can take out. And we can have 1 by omega L. And here we have a very unique combination. There is voltage harmonic divided by its own order. So now there is some weightage given to each harmonic. Say if we talk about fifth harmonic, it is weighted by 1 by 5. If we talk about seventh harmonic, it is weighted by 1 by 7. If we talk about 11th harmonic, it is weighted by 1 by 11. So we are giving more importance to lower order harmonic compared to the higher order harmonic. Understanding my point? So definitely a better way, because this is what we should have. This is what we should have, because these harmonics are more dominant, more harmful. Now still this equation has the fundamental current coming over here. So if I talk from the induction motor perspective, what I can say that this THD value, if you can find the worst ITHD, then any other value will be better than that, right? If you can find the worst ITHD value, and worst ITHD value means when I1 is minimum, which means when induction motor, if I'm talking about, is operating at no load operation. Under that condition, I will have minimum value of I1 and worst value of ITHD. So if I can keep my worst ITHD within limits, then I am going to find anything better for the further loading of the induction motor. Correct? Is this point clear?
Yes, sir.
Yes.
Yes.
Now quickly we can see the least value or the no load value of the current is basically nothing but the magnetizing current, more or less the magnetizing current which is flowing in the system. And we can approximately say that IM or I1 under no load is basically V1 by omega Lm. Because this is no load operation, so slip is going to be very small. This parallel branch will go out. Then this is a dominant impedance compared to the stator one. So only Lm will be remaining over here. So that will dictate what is the magnetizing current flowing in the system. Understanding my point? Then we have the ITHD. I will conclude the class in another 1 minute by completing this expression. Okay. Fine. So we have some value of I1 given in terms of V1 and omega n. So then I can write my ITHD, which is coming as 1 by omega L here. L is leakage basically. LLS plus LLR. Summation of Vn by n whole square, and then divided by this V1 by omega Lm. And this can be written as Lm by LL into, or here I can take a square root, Vn by n whole square divided by V1. This quantity, what you see over here, is also called as the weighted total harmonic distortion of voltage. because there is factor n coming everywhere with the harmonic. That's why this is called weighted THD of voltage. So the line current THD can be related in terms of voltage THD, weighted total harmonic distortion of voltage, as this. Where we know that WTHD doesn't involve any current, so this is independent of load. Which means a better way to have good performance for the system could be to minimize VWTHD, which will be independent of load and which will give a better performance for the, because it is directly related to our ITHD, worst case ITHD. Fine.
Yes, sir.
So I stop the class here. You may proceed for your next class. If there are any quick questions, you can ask. Okay, so I have extended the deadline for lab 1 submission up to Friday midnight. No later than that. Okay.